Okay, in this chapter, we will see the concept of stresses, strains, and theories of failure. Okay, so let's focus on concept of stresses first. Okay, so to understand the concept of stresses, we are actually going to see some continuum mechanics. Okay, throughout this chapter. Okay, stresses, strains. So first we will give short introduction about continuum mechanics. Okay, and before moving to this concept of stresses, we need to understand the very important concept, that is traction. Okay, so we'll see traction, then we will see concept of stresses, and then once we understand stresses, we'll extend our understanding uh, for principal stresses. Okay, so let's start with continuum mechanics. So what is continuum mechanics? So continuum mechanics is the branch of physics that deals with the deformation of the solid or body when it is subjected to external loads. So like let's say this is a body or solid, okay, and it has been subjected to some external loads, and when it is subjected to external loads, the body responds, right? So this response is nothing but deformation. Okay, so this continuum mechanics deals with the deformation, uh, characterization of deformation and quantification of deformation. Okay, so how it is deforming, characterization, and how much it is deforming, okay, quantification. So so uh, this is a difference. Okay, continuum mechanics is not about predicting the deformation. Okay, not predicting. This is FEA and our analytical calculations do this, predicting the deformation. Here we want to develop the measurements. Okay, develop measures to characterize and quantify this deformation. Okay, so we want to determine the measures, that those are nothing but stresses and strains. So hope you understood. The deformation response is characterized by and quantified by the stresses and strains, because when it deforms, it generates stresses and strains. Okay, so let's understand what is the continuum in continuum mechanics. Okay, so idea of continuum. Okay, let's take this solid body. Okay, B. Okay, so what is this body or structure? So we know this body has infinite number of particles, right, or points. So body is nothing but it is continuous distribution of infinite number of particles. Okay, infinite number of particles, infinite, and these particles are known as continuum particles. Okay, so let's try to understand continuum particle. Okay, so let's take this particular continuum particle. So continuum particle, okay, at macroscopic level. At macroscopic level means at the level where human eye can see. So at human eye level or macroscopic level, this particle is a point in a body, right? So for us it is a just point in a body. Okay, for a human at macroscopic level, so it obviously it is a point, so it has a zero length or size. Okay, we can say, and this point or continuum particle at macroscopic level is not a piece of material, it is just point, it is not a chunk of material. But at microscopic level, okay, when we zoom into this, when we like zoom to this, okay, this particle has finite size. So it can be length, area, or volume. Okay, let's say length. So at microscopic level, this particle has finite length L or size. So this is a very fundamental assumption in continuum mechanics. Okay, and based on this assumption, all the derivations are derived. All the concepts of stresses and strains are derived. Okay, so what is that? So we say like, okay, we want to find the stresses and strains at a point. Okay, here, but at microscopic level, we define a size. Okay, because uh, to derive something, okay, we need to define some size, then only we can define. So let's see those things, but let's understand this fundamental assumption. Okay, uh, so this continuum particle, okay, or point, it is possible to define size, as we say, at microscopic level. When we zoom into that, we can define some size. Okay, so how much is the size? So this size is smaller than the variation of quantities like stresses and strains. Okay, so we cannot take very big size like length L is not big enough that within that size, okay, the stresses and strains are changing, they are not constant. Okay, and it is clear like we want to find the stresses and strains at point. Okay, at a point, stresses and strain remain constant. So when we zoom into that point, okay, the stresses and strains or these quantities should remain constant. So we say it is smaller than the variation of quantities. Okay, so it is not big enough. Okay, so this is the upper limit. Okay, and lower limit, it is a larger than atomic scale. Okay, so it is not so small, okay, like at a atomic level. Okay, atomic level size. So it is just big enough that the variation of quantities, stresses and strains are constant. Okay, so before understanding or moving to our traction and stresses, let's understand some very basic concepts. Tensor. Okay, what is a tensor? So this is a textbook definition. There could be many definitions in different textbooks, but this is also from one of the textbooks which I liked this definition because it is very easy to understand. So what is tensor? Tensor is mathematical algebraic object to describe some quantity. Okay, let's say physical quantities. So based on the dimensions of tensor, it is called different names. For example, scalar, vector, and matrix. Okay, so let's say scalar first. The scalar is a zeroth order tensor. Okay, that means it is defined by only magnitude. Okay, so if I give example, it will be more clear. For example, pressure. Okay, we'll take mostly on solid mechanics perspective examples. Okay, otherwise electromagnetics or CFD also you can think of different scalar quantities, but let's understand for solid mechanics. So pressure is a scalar, right? Then length, okay, mass, temperature. So these are all scalar quantities or zeroth order tensor. Okay, so to define temperature, okay, you need only magnitude. Okay, we don't say okay temperature is changing in X, temperature is changing temperature about X, temperature about Y and Z. Okay, we just say at a point temperature there is a magnitude. Okay, we don't define it by direction. Similarly, mass and pressure. Pressure is also scalar. Okay, pressure is always normal to the surface. Okay, it is just defined by the magnitude only. Then comes a vector. Vector is first order tensor. Okay, that means it is defined by magnitude and direction. Okay, scalar magnitude only, vector magnitude and direction. For example, displacement, velocity, acceleration. Okay, and since we are talking about FEA, so displacement and force, these are the best examples we can understand. Okay, displacement and force. So we, to define a displacement, we have to say how, what is the magnitude of displacement in x, y, and z. Similarly, what is the force in x, y, z. Okay, so we need a magnitude and direction both. Okay, so we say u1, u2, u3, or ux, uy, uz, or fx, fy, fz. Okay, so we need to define a magnitude and direction. Then comes matrix. Okay, so matrix is a second order tensor. uh, Actually matrix is second, third, or fourth order tensor, they are all called matrix. Okay, but let's stick to second order tensor. Okay, so to define a matrix second order tensor, we need three quantities: magnitude, direction, okay, uh, plus another third quantity, uh, that is, sorry, third dimension, that is associated plane. Okay, so this will be more clear in concept of stresses. So let's for now just take take it as it is. Like for matrix we need magnitude, direction, and associated plane. So the examples, okay, for our FEA, they are stresses, strains, okay, stress, strain, displacement gradient, deformation gradients. This, those all are metrics. Okay, okay, so we'll see this uh, very clearly later. So now hope this is clear, and this is for your additional information. Okay, additional info. The dimensions required to define any tensor is equal to order of that tensor plus 1. Okay, so it is clear. Like for scalar, it's a zeroth order tensor, so you need one dimension, that is magnitude. For vector, it is first order, so 1 plus 1 equal to 2, so you need two dimensions, magnitude and direction. Here only magnitude. Matrix is a second order tensor. Okay, so dimensions required to define this matrix is 2 plus 1. Okay, so 3, so you need three dimensions: magnitude, direction, and associated plane.